We've all been there. You paste a massive PDF or a long block of code into a chatbot, ask a simple question, and nothing. The AI stalls out, hallucinations begin, or its logic just shatters entirely. That crash happens because you've hit the model's context limit, essentially the boundaries of its short-term memory. It can only hold a specific number of tokens at once before it starts dropping older information to make room for new data. Fixing that amnesia usually requires brute force. To expand an AI's context window, tech companies have to build out massive, multi-million-dollar data centers, filling entire rooms with physical server racks just to store the active data of a single long conversation. Physical storage requirements are currently the hardest cap on how much an AI can actually process at once. Engineers manage storage using vector quantization, compacting high-dimensional data into tiny, low-resolution blocks. But perfect compression requires a meticulous sorting process, taking hours, useless for real-time chatbots. Faster algorithms are brutal, chopping off so much precision the AI gets immediate amnesia. That brings us to a new mathematical approach called TurboQuant. Instead of carefully carving the data or blindly smashing it, TurboQuant treats data more like a vacuum seal bag. It shrinks the AI's active memory down to just 20% of its original size, and it does it instantly, without degrading the model's logic or recall. To see how it achieves this, look at how information actually sits inside a computer's memory. AI data naturally forms irregular, jagged clusters in high-dimensional space. Because these shapes don't fit together neatly, they leave massive gaps of wasted space. TurboQuant solves this with a two-step process. Step 1 is a random rotation. The algorithm takes those jagged data clusters and spins them rapidly along multiple intersecting axes. By mathematically shaking the vectors, it forces the data to smooth out. The chaotic coordinates redistribute themselves into a highly predictable, uniform pattern. Because the data now takes on a standard shape, the algorithm doesn't have to waste time figuring out how to organize it. It can instantly drop these uniform pieces into tiny digital boxes, leaving zero empty space. Mathematically altering the shape of the data, rather than deleting information to make it fit, allows the system to bypass the painfully slow processing times of older compression methods. But packing data this tightly introduces a new problem. The mathematical compression creates a tiny directional bias. It's a lot like packing a suitcase so tightly that your favorite shirt gets a wrinkle. To fix that wrinkle, TurboQuant applies step 2, the 1-bit polish. The algorithm adds just one single extra bit of data per coordinate. That addition is enough to perfectly correct the bias and align the data without adding bulk. To prove this actually works, researchers ran TurboQuant through the needle in a haystack test. This is an evaluation where an AI is forced to read a massive document and locate one specific hidden sentence. The results are striking. Even when the AI's memory was compressed by a factor of 4.5, TurboQuant maintained a 100% perfect retrieval rate. It performed exactly as well as a massive, completely uncompressed model. This data shows we can mathematically decouple the physical size of an AI's memory from the accuracy of its recall. To be clear, TurboQuant is still a form of lossy compression. Microscopic layers of absolute mathematical precision are permanently discarded to shrink the hardware footprint. In 1948, Claude Shannon established information theory, which proves there is a hard mathematical speed limit to all data compression. Past a certain point, no algorithm can squeeze data any further without destroying the information entirely. It is a physical limit of our universe. The math behind TurboQuant operates incredibly close to this limit. It achieves a distortion rate within a factor of 2.7 of Shannon's absolute theoretical boundary. It's an engineering milestone that brushes right up against the absolute limits of physics. This enables immediate upgrades to the KV caches inside chatbots, so they can remember incredibly long conversations, while also accelerating the vector databases that power global search engines. But zooming out, this level of compression indicates a shift for computing. Highly capable AI models will no longer require giant centralized server farms to hold their thoughts. We are moving toward a future where powerful, context-rich AI runs entirely locally on our laptops and everyday smartphones, holding entire libraries of information right in our pockets. We started with a crippling hardware bottleneck, and bypassed it by rotating high-dimensional data into a more efficient 5-fold compression that maintains accuracy. By re-engineering the spatial properties of data, we have unchained AI from the cloud, moving massive context directly into the palm of our hands.